right, so today we're just going to kind of go over an overview of types of things you may need to know for the geometry final. It's not super specific like a lot of our reviews have been. So our review is going to be in 4 little parts that are going to cover all 4 marking periods. Okay? So for marking period 1, the things we need to make sure that we're familiar with, and the reason we're doing all 4 marking periods is because it is a final. So it's not a semester exam, it's a final for the whole year. And in geometry, right, we use things all year long. So it's important that we still remember all of those skills. Okay? So in marking period 1, we're going to be talking about angle bisectors, angle addition postulate, parallel lines and transversals, segment addition postulate, and midpoints are all going to be covered. Okay? So, what do we know about angle bisectors? They split an angle into 2 equal parts. If I wanted to draw an example, I could draw an angle, and then I could draw an angle bisector in. And I would know that these 2 pieces are exactly the same size. So let's say one is 40, that means the other is also 40. Right? Sometimes you see angle bisectors used with algebra problems. So another way we see angle bisectors is we may have an angle that's bisected. And sometimes we'll see expressions like maybe 6x plus 3 and 8x minus 7. And I have to find x. What would I do in this case to find x? Yeah, I would set those 2 things equal to each other, right? I would do 8x minus 7 equals 6x plus 3. And then from there, I would just solve. I would subtract the 6x on both sides. So that would give me 2x minus 7 equals 3. I'd add the 7 to both sides, so 2x equals 10. So x equals 5. And then I could plug that 5 in here, right? And here. And make sure that it's right, because both of those angles would have to be the same size. So 6 times 5 is 30, and 30 plus 3, this angle is 33 degrees. 8 times 5 is 40. 40 minus 7 is also 33 degrees. Okay, so you could see it either way with just degrees or with algebraic expressions. Okay. The next topic you'll see on the exam is going to be angle addition postulate. What's the angle addition postulate? Probably has something to do with adding angles together. Like if I looked at this picture and I wanted to apply the angle addition postulate to this picture, what would I do? Add the angles together. 40 plus 40 would be 80, and what does that 80 represent? The whole angle, right? So for example, if I look at this one, angle addition postulate says if you have an angle that's divided into smaller angles, you can add those smaller angles together to get the whole angle. So if I do 40 plus 40 for this one, I'll know that whole angle is 80 degrees. Same thing over here on this one. If I do 33 plus 33, that's going to be 66. So I know this whole angle is 66 degrees. Angle addition postulate. Questions on that? Okay. Then you're going to have where you have to identify angles in parallel lines and transversals. So if I know if I have 2 parallel lines and a transversal, if I know one of the angles, let's say I know this angle here is, I don't know, 80 degrees. if these lines are parallel, can I find all the other angles in that picture? Yes. Well, starting with, if we don't have parallel lines, I can find those other 4 angles, right? How do I find the other 3 angles? How do I find the other 3 angles if I know one is 80?
Vertical angles.
Vertical angles, so they're both 80. And supplementary angles, because I have these linear pairs, right? So 80 and 100. So I have 180 degrees. 80 and 100, or another set of vertical angles. Okay? And then, what happens at that bottom intersection? They're all the exact same angles as the top intersection, right? Corresponding angle says if this one's 80, this one's 80. And then we can use all those same properties to find all of those angles. So if I know one corner, then I can find all the corners, right? If I know 1/4 corner, I can find all the corners. Okay? All right, the next one we're going to look at is segment addition postulate. So my angle addition postulate says if I have angles that are together, I can add them together to find out how big the whole angle is. Segment addition postulate says if I have segments together, I can do what with them to find the whole thing? Add them together. It's addition, right? Segment addition postulate. So an example, just with letters. If I have this segment, if I know how long one side of it is, and I know how long the other side of it is, to find the whole thing, that's going to be A plus B. It's going to equal the whole thing. Okay? So with actual numbers, let's do an example. Let's say I've got a 3 and a 5. How long is the whole thing? 8, right? 3 plus 5 equals 8. Okay? Sometimes we see these with algebra, just like we have our angle bisectors and we see angles with algebra. So let's look at one of those kind of examples in case we see that when we do our exam. So let's say I have 17x minus 18 and 9x plus 14. So that'll work out. And let's say I tell you the whole thing equals 100 units. How would I solve this one for x? Right, in order to find this whole thing that equals 100, I know I have to add the left side, 17x minus 18, plus 9x plus 14. So that's going to be 100 equals 17x plus 9x is how many x's? When I combine these like terms. 26x. And then negative 18 plus 14 is negative 4. I'm going to add 4 to both sides. And then I'm going to divide by 26. So it's 104 divided by 26. 4. Okay. How could I check that if I wanted to check it? Yeah, I could substitute the 4 back into both sides, and then if I add them together, it should add up to 100. Okay? Midpoints. What's a midpoint? A point on another line. Let's go with a segment. There's no middle to a line because the line never ends. A point on a segment. Where is it? Where is the midpoint? Exactly in the center. It has to be equal distant from each end, right? It's exactly halfway in the middle. Okay? So, when you see it, if it's a midpoint, then however long one side is, the other side's the same. I just chose a random number. Both sides are 5. So you can either have numbers like that tells you M would be a midpoint, or you might have what signifies 2 segments are the same length? Tick marks. You might see tick marks. If I look at that last example that I did and I say, is this point a midpoint? It doesn't look like it's a midpoint, but am I allowed to tell by looking if this is a midpoint or not? No. If I wanted to know if this was a midpoint, let's call it X, and I said, is X, this one, a midpoint? How would I find out if that's a midpoint? Yeah, I would do what I said I would do to check. I would substitute the 4 into both places, right? I would do 17 times 4 minus 18. So 17 times 4 minus 18, let's grab a calculator. 17 times 4 minus 18 is 50. Is this going to be a midpoint? If it's 100 all the way across and I've got 50 on one side, how much do I have to have on the other side? Yeah, this side better also be 50. 9 times 4 plus 14 is also 50. So even though I didn't draw it like a midpoint, is it a midpoint? Yes, because we can mathematically prove it is. Because these two are equal to each other. Questions? That's everything you need to know for marking period 1. Basically doing like geometry in a year in a day. Okay. All right. Marking period 2, we learned about congruent triangles and we learned about relationships in triangles. Okay. How to apply Cpctc. Does anybody remember what stands for? No? I mean, that's how I would pronounce that. But does anybody remember what it stands for? It's not cuddle puppies because they're cute, but they are, and I would cuddle them if there was one here. Cpctc. Close. Corresponding parts. Of, so that's CP, now I've got CTC. Congruent triangles are congruent. Okay? So let's say I give you the following 2 triangles. I give you this triangle, and I'm going to tell you this is 3, and this is 3, and this is, I don't know, 64. And I'm going to call this triangle A, B, C. And then let's say I have another triangle over here, and I'm going to call this triangle D over here on the right-hand side, E up at the top, and F over here on the left. And then let's say I say triangle ABC is congruent to triangle DEF. And let's say I say find the measure of angle E. Now, if corresponding parts and congruent triangles are congruent, I need to use this statement here to tell me what parts match. tell me what parts match. Okay? So for example, the first letters are A and D. So I know that A matches with D, even though I didn't draw it so that it looked like that. Okay? B matches with E. B matches with E. And C matches with F. C matches with F. How big is angle E? E matches with B. E matches with B. So E is 64 degrees. What if I said, how big is, find the measure of angle let's go with F. F matches with C. What kind of triangle is this? Why is it? How is it a right triangle? I don't see a little box there. How is it an acute triangle? I mean, I only know one angle so far. Yes. I can't hear. It is isosceles, right? Two sides are the same. So what if I have two sides that are the same, what do I know about angles? Two angles at the bottom of those sides are the same, right? So if I start up here where the two sides that are congruent meet and I go out to the bottom, I know both of those are 64, right? So this is 64. C matches with F, so F is 64. Measure of angle F equals 64. Oh, look, I put percent there. It's not a percentage, it's a degree. My brain is still doing probability. Degrees, not percents. All right, let's say I wanted to find the measure of angle. What have I not found yet? Angle D. Find the measure of angle D. How am I going to find angle D? Well, yeah, 180 minus 64 minus 64, because I know those other two angles in there are E was 64, F was 64, so the one I'm missing, D, I know the three angles in a triangle have to add up to 180, so if I do 180, and I subtract those two 64s, that leaves me with 52 degrees for angle D. 52 degrees for angle D. So I did percent again. So this triangle is not a right triangle. It's what kind of triangle? It's acute. All three angles are acute. It's an acute isosceles triangle. Okay? All right, something else we're going to need to be able to do is identify an altitude, a median, an angle bisector, and a perpendicular bisector. So I'm going to go ahead and just draw 4 triangles. I'm going to make them scalene. So that it's kind of leaning a little to the left a little bit. Because if you make them isosceles, then some of them overlap each other. We want to see them all different. All right, so if I want to draw in an altitude, I'm going to put it at this first triangle. It starts at a vertex, and it goes to a 90-degree angle. So pick one of your corners. I'm just going to, on each time, start at the top corner. And I'm going to go to the opposite side at a 90-degree angle. Your altitude is just your height. Remember, you can draw these from all three angles, right? The intersection would be the orthocenter. Okay? For the median, your median also starts at a vertex, and it goes to a midpoint. So if I start here, then what I'm looking for to find the midpoint is I need a side that's got a point and tick marks. So I can say, oh yeah, that's a midpoint, or some way to show that that's a midpoint, right? That is a median. Angle bisector, I'm going to do in green, and I'm going to put it on this one. An angle bisector has to start at a vertex, and I have to see congruent angles. So I have to leave this vertex or any of the vertices, and when I do, I have to take that whole angle and I have to divide it in half. Sometimes you'll see it as a ray. You could also see it as a segment. It could also be a line that goes all the way through. How do I show that the angles on both sides are the same? What symbol should I be looking for? I should be looking for arcs. Oops, I almost drew it in the wrong picture. The little matching arcs. So in this one, I should be looking for a corner and a little box. This one, I should be looking for a corner and the midpoint symbols. This one, I should be looking for a corner and arcs. And so then last but not least, my perpendicular bisector, which I don't know why it didn't get capitalized. It just didn't. Everything else did. Perpendicular bisector is the only one that doesn't have to go through a vertex. The other three all have to go through a vertex. It has to bisect, so it has to go through that midpoint. So I have to find my tick marks. And then it also has to be perpendicular, so it has to go straight up or straight down. Sometimes you'll see it as a line. Sometimes you'll see it as a ray. Sometimes you'll see it as a segment. It can be any of the things. Okay? Perpendicular bisector. So it has to be midpoint at 90 degrees. It does not have to go through the vertex. That's the whole semester. Yay! Semester 1 done. Let's look at semester 2. Marking period 3, we did similar triangles, we did right triangles, and we did quadrilaterals. The first thing it says are what are the properties of the angles and the diagonals in parallelograms. So I know when I have a parallelogram, I'll sketch myself a little parallelogram. I know the opposite angles are going to be congruent to each other. So however big this one is, the one opposite it is the same. However big this little one is, the opposite one is the same. And I know angles on the same side are supplementary. So if I add these two angles together, they should add up to 180. For the diagonals, there's only one property about diagonals in a parallelogram. You usually have one that's longer and one that's shorter, unless your parallelogram is a rectangle or a square. But the pieces are bisected. So one piece is divided into two equal pieces, and the other one's divided into two equal pieces. One does not have to equal the other. Right? That's why I put different tick marks on them. Okay? Let's talk about our specific types of parallelograms. Let's talk about the rectangle, the rhombus, and the square, and make sure we're familiar with those properties. For a rectangle, the properties of its angles are what? On a rectangle. They're all 90. 90, 90, 90, 90. The properties of the diagonals are still the same as this one. My opposites are bisected. But because I've shifted and now they're 90 degrees, those diagonals are also congruent. So instead of having different tick marks, the diagonals are congruent. So all four of those little pieces are the same. on the rhombus, when I draw a rhombus, little diamond thing, my diagonals bisect the angles. So these two angles here are the same, and because opposite angles are the same, these two are the same. And then this diagonal bisects those angles. So these two angles are the same, and because opposite angles are congruent in a parallelogram, these two angles are the same. And then the properties, so those are the properties of the angles on the outside, right? And then the properties of the diagonals, in addition to they bisect each other. The other thing we need to know about the diagonals is when they intersect perpendicularly. So you end up with 4 little right triangles, which is maybe important because this unit also, or this marking period also included right triangles. So with one picture you could hit both of, actually really all 3 of those, right? Because you can use Pythagorean Theorem and Trig with the same triangle. Alright. And last but not least, a square. My square is all 4 sides are the same. My angles, because it's a rhombus, my angles that are 90 because it's a rectangle get divided into 45s for every square. Oops, I missed one. And because it's a rhombus, I know that center angle is a 90, so I end up with a bunch of little 45, 45, 90 triangles. Notice this doesn't say anywhere that we're using special right triangles, so you probably shouldn't expect to see a 30, 60, 90 triangle or a 45, 45, 90 triangle. So perhaps there's not a square. Perhaps it's a rhombus or a rectangle. Alright, so then it says use trig to find an angle in a right triangle. So when it says find an angle, when I see find an angle, using trig with finding an angle, that was all of my inverse trig. That's all my inverse trig. We're going to need to make sure we remember, so ka, toa. If I'm trying to find an angle, let's say I want to find in this right triangle, because trig only works in right triangles. Let's say I want to find this angle up here. And if I know, let's say I know this side is A and this side is C, whatever those numbers are. If I want to find x, I would put my smiley face here, and I would say that means this is my hypotenuse, this is my adjacent, so this is my opposite. So that angle, x, is going to equal the inverse sine, cosine, or tangent. If I know A is the opposite and C is the hypotenuse, if I have numbers for those two sides, sine, opposite and hypotenuse. So the inverse sine of the opposite over the hypotenuse. If I'm trying to find an angle, and I have B and C instead of A and C, my smiley face is here. This is still my hypotenuse. Now here's my adjacent. This is opposite. So x is going to equal, sine, cosine, or tangent if I'm working with the adjacent and the hypotenuse. Cosine. Cosine. Inverse cosine of the adjacent over the, b, over c. So the only one we haven't looked at is tangent, so let's look at a tangent example. Do you want to see one with actual numbers? Yes or no? Yes? So we'll make up numbers for this one. Oops, I forgot to put my right angle in there. Let's say this is x, and the opposite is, give me a small number, 5. And the adjacent is, how much? 15. Did you say 15? My picture is not to scale. That's okay. My picture doesn't have to be to scale. Alright, so to do this one, here's my smiley face. So my x equals, this is my hypotenuse. I don't know what it is. I could use Pythagorean Theorem to find it out if I really wanted to, right? I have enough information here to find my hypotenuse. This is adjacent, right? We know that's adjacent because the two sides that come out of the smiley face, one's the hypotenuse, the other is adjacent, so this is opposite. So this time I know my opposite, I know my adjacent, so I'm going to use inverse tangent. Of the opposite is 5, over the adjacent is 15. So this angle is, nope, escape, trig, right? You have your trig button right there, trig. And we want the second row. Let me brighten this up a little bit, right? Because the second row is the one that has those little negative ones. The inverse tangent of 5 divided by 15. You could reduce the fraction to 1/3, but you don't have to. The calculator, they've got it. So, it's a really tiny angle, but it makes sense because one side is, that side is much shorter than this side, right? So hinge theorem says this side is not going to be very big. That side is only 0.322 degrees, that angle. It's a teeny tiny little degree because we picked a really long side with a short side. Okay? Questions? Okay. The next topic that you'll see, or another topic you'll see in this section, is Pythagorean Theorem. So most of y'all can use Pythagorean Theorem. A squared plus b squared equals c squared, but remember I had given you the shortcuts and I had said the hypotenuse is equal to the square root of your two legs squared and added together. The leg, if you need to find a leg, is the square root of your hypotenuse squared minus the other leg squared, A or B. Remember, the important thing is put the bigger side in first, especially on this one. It doesn't matter so much on the hypotenuse, but on this one it's going to matter when you're looking for the leg because you have to put in your hypotenuse squared first. So it'll give you an error if you get that backwards. Okay? Alright, the next one, use a similarity statement to identify similar sides and to find a scale factor. Okay, so let's say I have two triangles because they're easy to work with. And one looks like this, where I know this piece is 3 and this piece is 15. And then B, A, C. And then let's say I have another triangle here. And let's say this is 4.5. This is D, E, and F. And I tell you triangle ABC is similar to triangle DEF. I'm going to ask that we find the scale factor and the distance from E to F. Alright, so the first thing, if I want to find the scale factor, to find the scale factor, I want to find two sides that are corresponding. And on the second triangle, I only have one side. I only have the distance from E to D is 4.5. So I'm going to have to work with E and D. That's going to match what side on the other triangle? Which one? A and B. So those two sides are going to match. I can use those two to find my scale factor because they're corresponding. Since my scale factor, or since my similarity statement is written with ABC first, that's how I'm going to do my scale factor. So my scale factor is going to equal from ABC, I'm going to put that in my numerator, 3 over FED, I'm going to put 4.5. Now your scale factor generally does not have decimals in it, so there's two ways you can go about reducing this. You could say, well, to move that decimal over 1, I multiply everything by 10. And then I would reduce that. 15 goes into the top 2 times, and 15 goes into the bottom 3 times. So my scale factor is 2/3. Or another thing you could do is you could put it in your calculator, 3 divided by 4.5, and then you could go to menu number and tell it, can you take the approximate answer you were going to give me and make sure it's a fraction? And it'll give me 2/3. And that's only necessary if you have a decimal. I don't think tomorrow there's going to be a decimal, or whenever your final is scheduled. I don't think there's going to be a decimal. Alright, so that's the scale factor. But we're also supposed to find the distance from E to F. So E to F matches with what? B to C. B to C is the 15th. Okay, so remember this was my up arrow, so that 15 is going to go in the top. Over, that means this is my down arrow. I'm trying to find the distance from E to F, so I'm going to call it X. I know this fraction is going to reduce to what? To what? 2/3. I could also just set it equal to, I could do 15 to X equals 3 to 4.5 and cross multiply with those numbers as well. I would get the same answer. 2 times X is 2X, and 15 times 3 is 45. Divide both sides by 2, and X equals 22.5. For EF. I should say equals EF. Alright, and then we have this last marking period that should be freshest on our mind. Use coordinate notation to rotate. So, that means we're going to be given a point, right? And we're going to have to rotate it either 90, 180, or 270 because those are our only options. So, what I would do is I would write the rules. Let's see, I'm going to rotate, as an example, the point. Anybody have an idea for a point? Little numbers. Maybe a negative. 2, 3. How about negative 2, 3? Just that way we can see what to do with negatives. Rotate negative 2, 3 by all of them. We're going to do 90, we're going to do 180, we're going to do 270. So 90 degrees. If I look at my formula chart, it says XY becomes the opposite of Y, X. 180 says XY becomes the opposite of x, the opposite of y. 270 says xy becomes y, the opposite of x. Alright, so if I start with -2, 3, when I rotate that 90 degrees, -2, 3, the opposite of y is going to become -3, and x is -2. So notice the signs here don't necessarily have to match, right? These are both negative, but this one's positive, this one's negative. Okay? 180 says take that original point, the 2, 3, and it becomes the opposite of x. X is -2, so the opposite is +2. And the opposite of y, so -3. And then last but not least, -2, 3 for 270 degrees becomes y, 3. The opposite of x, +2. And again, you'll have your pink formula charts, so you don't have to memorize the rules. You just have to be able to apply them. Okay? The next one, identifying and finding the base of a 3D figure, because remember we said it's all about that base, because if you can't find the area or the perimeter, if you can't identify which side is the base, that becomes an issue. Okay? So here is what I'm going to draw for my first example. I'm going to do 3 little drawings for examples. I'm going to draw a little triangle. And then from the top corner, I'm going to do a little segment that goes backwards. Try to do it a little step at a time because I know we're not all artists. And then I'm just going to duplicate this segment. I'm going to duplicate it back here. And I'm going to connect here. So I made like a little tent. In geometry, we do like to draw the parts that we can't see as dotted lines. So I would just match this line here with a little dotted line. And then I would match this line here with a little dotted line. And then you just connect. And look, we all just drew a 3D prism. Yay! What's the shape of the base on this 3D prism? It's a what? It's a triangle. So we've identified the base. The base is a triangle. So if I had to find the area of the base, we would use the formula 1/2 the base of the triangle times the height of the triangle, right? And remember, the height of the base and the height of the prism are 2 different heights. They both use a lowercase h, but they're 2 different things. Okay? Let's say this next one's going to be fun to draw also. I'm going to draw a little pentagon. A little pentagon. From the left-hand corner, I'm going to draw a segment that comes down. And then I'm going to mirror these bottom 3 segments. I'm going to come down. I'm going to come parallel. I'm going to come up parallel. And then I'm going to connect. 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 And then to draw the pieces that we can't see, I'm going to mirror this piece here. And I'm going to mirror this piece here, dotted. And then I'm going to connect from where those came together to the top. And we drew a 3D prism. What's the shape of my base? Pentagon. I've got this one down here in the bottom. And this one up here on the top. This is a pentagonal prism. The base is a pentagon. Do you remember the formula for a regular pentagon? Yeah, 1/2 little a capital P. Remember, your little a is your distance right there. All right, for my last one, I told you we'd do 3. For the last one, I'm going to draw a circle. And then from the top leftish corner, I'm going to draw a segment that goes back. And then directly across from that, I'm going to draw another segment that goes back. And then I'm going to draw this part of the circle solid and then make it dashed. What's the shape of my base? A circle. It's a cylinder. So the area of the base is pi r squared. Oh, we're not going to have time to get to the last one. Find the probability that a point will land in a specific part of a 3D figure. So what that's going to be like is if you have, for example, maybe a prism, like a cube. We won't have time to get through it, but I'll try to sketch a picture real quick. Let's say I have a cube. And then inside that cube, there's another shape. Let's say there's a sphere that fills up the whole thing. If I want to find the probability that a random point lands in the sphere, then that's going to be the volume of the sphere over the volume of the prism. Right? And I'd have to use my volume formula for the sphere and my volume formula for the prism, and sphere over prism. Questions? Okay. Yes. Hold on.